to increases in retention and factors that lead to decreases in retention. And if you only remember one thing, anything that enhances the water solubility of a solute, any functional group that makes it more soluble in water, will lower its retention in reverse phase chromatography. So really polar functional groups, and especially functional groups that are very, very good hydrogen bond acceptors and donors, will really enhance water solubility and have a big effect on retention, and will lower retention a lot. The other thing we talked an awful lot about was the organic modifier. That's the stuff that you mix with water that allows you to vary retention. The more organic modifier, the lower retention. Generally speaking, I'm going to show you some exceptions to that quite soon. But the common modifiers are methanol, acetonitrile, THF, isopropanol. They need to be fully miscible with water. You don't ever want to be pumping a two-phase system through your column. You'll never get reproducible results. It will drive your detector crazy. You don't want to do that. And generally speaking, a plot of the logarithm of the retention factor, not the logarithm of the retention volume, not the logarithm of the retention time, but the logarithm of the retention factor, is reasonably linear function of the volume fraction of the organic modifier, not the mole fraction, not the concentration of the organic in moles per liter, but the volume fraction of the organic modifier. It's not an exact relationship, but it's a pretty good relationship. Generally speaking, the bigger the molecule is, the bigger the slope of that plot is. So for instance, as you go up a homolog series, that slope increases. As you go from a monomer to a dimer to a trimer, up a series of polymers, the bigger that slope is. For big polymers, be they synthetic or organic or biopolymers, you can see slopes there that are 20, 30, 50, meaning that those compounds are exceedingly sensitive to minute changes in the mobile phase composition. One or two more comments about what you mix with water. Since more often than not, the detector that we use in LC is a UV visible absorbance detector, you don't want your organic solvent to absorb light in the UV or visible range. That means that you have to work above a certain wavelength. For instance, water acetonitrile, you can work down at 210 nanometers, which is pretty far into the UV. Water methanol is a little bit higher, maybe 220, 230 nanometers. Water THF is a little bit higher than that. It's all important issues. I mean, if the further into the UV you can get, the more compounds, generally speaking, you can see. But you don't want to see your organic modifier, so there's some trade-offs there. The other factor is the following. The organic modifier has a big effect on the viscosity of the solvent. Rather big effect. And in fact, if you start with pure water and you add some organic solvent, generally the viscosity goes up. It goes through a maximum and comes back down. Isopropanol, that maximum is quite high. It's on the order of 3 centipoise. It's 3 times the viscosity of water alone. That means that your pressure drop is going to be 3 times higher. That means that your maximum velocity is going to be 3 times lower. So the chromatography at that maximum point is going to be 3 times slower in a methanol, in an isopropanol mixture than in pure water. that is at the worst point in the isopropyl mixture. So viscosity is another issue. Some solvents form very high viscosities with water. Ethylene glycol, for instance, would be a great co-solvent for water in reverse phase, but the viscosity would kill you. You just couldn't deal with it. DMSO, very interesting material, but the viscosity will just kill you. So methanol, acetonitrile, THF are used 99.9% of the time. There are differences in selectivity as you go from one solvent to another. We'll talk a little bit more about that today. Okay, so let me start the stuff for today right here. In fact, sometimes a plot of log K prime versus the volume fraction phi is nonlinear. In fact, it'll come down roughly as a straight line, and then it'll curve over, go through a minimum, and sometimes it'll even come back up. But that is not uncommon, but it's not common. Another issue is, how do you measure the dead volume? In gas chromatography, you can almost inject a little methane. Methane is at 50 degrees centigrade, is not retained on anybody's stationary phase, really. And so you can always measure your dead time of your system by injecting a little methane. But we have a much more difficult time finding something that's unretained in reverse phase chromatography, and I'll show you some of the choices. Then we'll talk about the effect of salt. When we add salt to the mobile phase, what happens to retention? In particular, we're going to talk about neutral or uncharged analytes. The effect of salt on an uncharged analyte is not big, unless it's a really big molecule, and then maybe there'll be a big effect. The effect of salt on anions and cations is another story. So we're just going to talk about the effect on neutral solutes today. Then we're going to look at the effect of temperature of the column. The effective temperature in LC is a lot less than in GC. But it's not negligible. It does matter. And if you don't control the column temperature, you're not going to get reproducible results. In the early days of LC was so irreproducible, that people didn't pay much attention to temperature because 1 or 2 degrees just don't matter much. But we now know how to do LC sufficiently reproducibly that the temperature does matter, and so it is necessary to control the column temperature. You'll see that the mobile phase pH has a humongous effect on the retention and selectivity of things that can ionize, like acids and bases. Is a very profoundly important variable in reverse phase chromatography and ion exchange chromatography. If you thought I'd have everything there is to say at this point about the mobile phase, that would be wrong, because there are some very interesting things related to what we call mobile phase additives. I differentiate between a mobile phase modifier, which is a co-solvent, methanol, acetonitrile, THF, and an additive. The modifier is present in high concentration. Additive is probably present in millimolar, maybe 10, 20 millimolar concentration, and it will have a profound effect on certain solutes, not necessarily all solutes. So this is definitely a way to manipulate selectivity. One of the things related to certain kinds of additives is what happens if you exceed what we call the critical micelle concentration. If you actually form micelles, and I'll show you what they look like in the mobile phase, that can have a tremendous impact on what you see in terms of retention. So the factors that influence your retention and selectivity in reverse phase chromatography are, number one, the percent organic. The amount of organic can change relative retention. The type of organic can change relative retention. The temperature can have a small but sometimes very dramatic effect on retention and especially selectivity. For compounds that are very close together, temperature sometimes can kick them apart just enough to make the separation a lot easier or a lot more difficult. I forgot to put pH on this list, but for ionic species, acids and bases, the pH can have a really humongous impact on selectivity. And last, the chemical nature of the stationary phase will have an impact on selectivity. I'll show you each of these as examples of each of these. And I certainly will not be able to get into different kinds of reverse phases today. That will have to take up on Monday. So this is the big picture for today and for the next lecture. Okay, nonlinear plots of log K prime versus phi. This may happen when you have a really polar analyte, something like glucose with 5 or 6 OH groups. Any biochemist, how many OHs does glucose have?
Should be 6.
Yeah. 6. That's pretty polar. Okay. Another type of solute that has a big effect is whether you have an ionized amine or not, and these sorts of issues can lead to a curved plot. By curved plot or nonlinear plot, log K prime versus phi, there's 0, there's 1, and so generally speaking, it's a straight line, but it may do that. It may curve positively, and generally, this is at a fairly high value of phi. I really don't expect to see this until phi is maybe 0.7 to 0.8. And when you do see this kind of behavior, it's generally on a reverse phase that has a lot of unmodified SiOHs. So that the extent of derivatization might only be 2 micromoles per square meter, not 3.5 or 4 micromoles per square meter. It's going to happen more when you don't end cap the stationary phase. But it certainly has been observed, and people who've seen it initially were quite disconcerted by it, but we've become accustomed to it now. Okay, in a lot of the plots I've shown you, we plotted K prime. To measure K prime, you need to know when an unretained species is going to come out of the column. So in reverse phase chromatography, there are a number of species which people have said are not strongly retained. I don't want to say they're unretained because I don't believe that they're absolutely unretained. But molecules like uracil and thiourea are very nicely UV active, so you can inject a small amount. However, if you vary the mobile phase composition, you will see small changes in the retention of these species. Something that's less retained is something like nitrate. Nitrate gives a beautiful UV signal at low concentration. So does dichromate. But if there's a charge on your stationary phase, either negative or positive, If it's a negative charge on the stationary phase, nitrate and dichromate will be repelled from inside the pore. If there's a positive charge on your stationary phase, nitrate and dichromate will be attracted into the stationary phase, and the retention volume is not the dead time. It's not the dead volume of the column. Another thing that's done is to inject as a solute deuterated mobile phase, and you need to use a refractive index detector, but you will see the deuterated substance in if the mobile phase has a lot of the hydrogenated substance. There's enough of a difference in refractive index. If you deuterium label your organic modifier or your water, you will get a refractive index peak. So using deuterated water and using deuterated acetonitrile, this is the deuterated water. If you change the mobile phase from low acetonitrile to high acetonitrile, you will see some variation in the water peak. If you inject deuterated acetonitrile, you will see some variation in the acetonitrile peak, and it will not have the same retention volume as the water peak, even though these things are your solvent. Why does this happen? It happens because even water and even acetonitrile adsorb into the stationary phase. And the amount that adsorbs depends upon what the concentration of the eluent is in the mobile phase. But there's not a lot of adsorption, but there's the very definite adsorption of water, acetonitrile, methanol, especially THF, into the bonded phase. There's no doubt about this. Now there's a theory of adsorption that tells us if we take the retention volume of the deuterium oxide peak and multiply that by the volume fraction of the water in the eluent, and add to that the product of the retention volume of the labeled acetonitrile times the volume fraction of acetonitrile, the theory says that that should be a constant, and that number is your best estimate of dead volume of the column. And that's this computed result here. And you can see that it really doesn't vary very much over a wide range in mobile phase composition. So this is the best way to measure the dead volume if you're doing really fundamental theoretical studies. Don't waste your time doing this if you're just looking for a quick and dirty understanding of what's going on. You can use thiourea, you can use uracil, but you're not going to get beautiful results. If you do, you'll get useful results, but they'll be complicated by the fact that uracil's retention does vary with mobile phase composition. If you want a rough and ready estimate of a retention factor, use uracil. Use thiourea. Yeah, Ryan.
The V score is with respect to D2O, but the V is not.
It's this peak. You measure this peak right there. That's the retention volume of D2O. And you also, obviously, to use this approach, you also have to measure the retention volume of the deuteroacetonitrile. You've got to measure that and put them together according to this, and you'll get that number. Okay, moving on. Here's the effect of salt, specifically potassium chloride, on a whole bunch of essentially neutral compounds. You see that for all of these compounds, as you add potassium chloride, there is a gradual increase in retention. This is a plot of the natural logarithm of retention versus the moles per liter concentration of potassium chloride. A mole per liter is a lot of salt. We almost never have anything like this amount of salt in small molecule chromatography. The effect of the added salt on small neutral compounds is not big. It's real, but it's not big. Potassium chloride is not the most, if you're trying to make this happen, potassium chloride is not the most effective salt. In fact, biochemists have looked at this very seriously. This tau value is the slope of the natural log versus the molar concentration of the salt that's added. You see that potassium chloride actually has the lowest slope, and something like tribasic citrate has the highest slope. This coefficient is known as the salting out coefficient. If you had a good undergraduate organic lab course, at some time, I know you did this, you use a solvent that's not terribly water